Here's a classic puzzle. Which fills first, 3D or 4s? The answer might surprise you. Electrons go into 4s before 3D. Why? Stick around. By the end, you'll be able to explain it clearly. In this video, you'll learn what s, p, d, and f orbitals look like, how many there are, how their energies compare, and how the Aufbau Principle and Hund's rule guide electron configurations. Here is a big idea. Orbitals are 3D probability clouds where electrons live. Each orbital holds up to 2 electrons with opposite spins. Shells are labeled by N. Within a shell, subshells are S, P, D, F. Let's build a clear picture of orbitals, step by step. First, think about shapes. The s orbital is spherical, and there's only one s per shell. In contrast, p orbitals come as 3 dumbbells, oriented along x, y, and z. Moving up, d gives us 5 orbitals, mostly 4-lobe clovers, plus the distinctive dz squared with a ring. And f expands to 7, with more intricate patterns. As the principal quantum number n increases, these orbitals grow in size, and for s orbitals specifically, radial nodes step up regularly. 1s has 0, 2s has 1, 3s has 2, and so on. To ground this, consider n equals 2. There's one 2s orbital, which holds 2 electrons, and 3 2p orbitals, which together hold 6 electrons. Add them up, and the n equals 2 shell can accommodate 8 electrons in total. One quick caution. Don't confuse subshells with orbitals. The p subshell contains 3 orbitals for 6 electrons overall, but each orbital still caps at 2. And remember, orbitals aren't little planets on tracks. They're probability clouds describing where electrons are likely to be. So far, we've covered shapes, how many orbitals each subshell has, and node or size trends as n increases. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide, then jump right back into the video. Lock in what you learned and keep going. Now, with shapes and counts in place, let's connect them to energies. Generally, as n increases, so does energy. And within a shell, the order runs S, then P, then D, then F. However, the way electrons actually fill follows the Aufbau principle, neatly captured by the n plus L rule. Orbitals with lower n plus L fill first, and if there's a tie, the orbital with the lower n fills first. That is why 4s fills before 3d in neutral atoms. Now, put this into practice with oxygen. Its electron configuration is 1s2, 2s2, 2p4. We first fill the 1s orbital, then the 2s, and then move into the 2p set. By Hund's rule, we place 1 electron in each of the 3 2p orbitals before pairing. This spreads electrons out and minimizes repulsion, so the result is 2 orbitals with a single electron each, and 1 orbital with a paired set. A common mistake here is pairing too early in p or d sets. Hund's rule reminds us to maximize unpaired, parallel spins before pairing them up. Next, let's look at a transition metal example, scandium. Its configuration is argon 4s2, 3d1. Notice how 4s fills before 3d in neutral atoms. But when ions form, the rules shift. Transition metals usually lose 4s electrons first because the relative energies shift once the 3d begins to fill. There are also subtle exceptions like chromium and copper, where extra stability comes from half-filled or completely filled subshells. But overall, the Aufbau Principle and Hund's rule work together to predict most electron configurations accurately. So in one breath, you've got orbital shapes and counts, the Aufbau order, 4s before 3d in neutral atoms, and Hund's rule to guide spin placement. With those tools, electron configurations read like a map.
Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.